every system of linear equations you'll ever meet. Hand it to a matrix, and its solutions arrive in exactly one of three flavors. Picture the flat plane, and let a matrix be the machine that reshapes it. Sometimes the answer is a single point. Sometimes it's a whole line or plane of answers, infinitely many. And sometimes there's no answer at all. The system contradicts itself. Which fate you get is decided by two numbers you can read straight off the matrix: its rank and its nullity. Count those two, and you know a system's whole story before you solve a thing. Let's fix the setting. A system of equations is just one matrix equation. Ax equals b. The matrix A holds the coefficients, x is the stack of unknowns, and b is the column of constants on the right. Say A has m rows and n columns. Then m counts the equations, and n counts the unknowns, one column for each. Keep that firmly in mind. N, the number of columns, is the star of everything that follows. Here's the intuition in one breath. The rank counts how many directions the matrix genuinely pins down, the independent constraints. The nullity counts the leftover directions it can't see, the free ones. Constrained plus free. Now let's make each precise. Start with rank. The cleanest way to find it. Row-reduce the matrix to echelon form and count the pivots, the leading non-zero entry in each non-empty row. That count is the rank. Here's a matrix already in echelon form. Two rows lead with a pivot. The third row is all zeros and leads with nothing. So two pivots, the rank is 2. But rank means something far richer than a tally. It's the dimension of the column space, the span of the matrix's columns. It tells you how much room the columns actually fill. Picture 3 columns living in 3-dimensional space. If all 3 happen to lie flat in a single plane, then no matter how you combine them, you never escape that plane. Their span is that plane, a 2-dimensional sheet. So even with 3 columns, the rank is only 2. Rank measures the dimension the columns reach, not how many columns you were handed. Now nullity, and it has a gorgeous picture behind it. Look at the homogeneous system. Ax equals the zero vector. The set of all solutions is called the null space of A. Its dimension is the nullity, and it equals something you can just count when you solve: the number of free variables, the unknowns you're allowed to set to anything you like. Geometrically, the null space is the collection of directions the matrix crushes flat to the origin. Take a vector x that sits in it, apply A and watch it collapse. The whole arrow gets flattened down to a single point at the origin. Anything the matrix sends to 0 lives in the null space, and the more such independent directions there are, the bigger the nullity. Now the centerpiece, the rank nullity theorem. For any matrix with n columns, the rank plus the nullity always equals n. Every single time. Read it as a conservation law. You feed n dimensions into the matrix. Some survive. The rank, the dimensions it keeps. The rest get crushed to 0. The nullity, the dimensions it loses. Nothing vanishes unaccounted for. They must add back to n. And the reason is almost embarrassingly simple. After row reduction, every one of the n columns is either a pivot column, it adds 1 to the rank, or a free column, it adds 1 to the nullity. There's no third kind. Sort n columns into 2 bins, and the 2 counts have 2 sum 2n. Let's make all of this concrete with a full example. Here is a 3 by 3 matrix A. We'll find its rank, its nullity, its null space, and then solve an actual system with it. The whole journey. First, clear below the leading one. Row 2 is exactly twice row 1. So row 2 minus to row 1 wipes it out completely. A full row of zeros. That's our first clue: the rows aren't all independent. Then row 3 minus row 1 gives 0, minus 1, minus 2. Now the first column is clean below the pivot. Swap the 0 row down to the bottom and scale the new second row by minus 1 to make its pivot a positive 1. We're almost there. Finally, clear the 2 above the second pivot, row 1 minus to row 2. That lands us in fully reduced form. 1, 0, minus 1 on top, 0, 1, 2 below. Now just read it off. Pivots sit in columns 1 and 2, so the rank is 2. The matrix has 3 columns, so n is 3. And rank nullity hands us the nullity for free. 3 minus 2 is 1. 1 free direction, so we expect the null space to be a single line. Let's actually find that null space. Set a x equal to 0 and read the reduced rows as equations. The first says x1 minus x3 is 0, so x1 equals x3. The second says x2 plus 2x3 is 0, so x2 is minus 2x3. Notice x3 is the free variable. Nothing pins it down, so let it be any number t. Then x1 and x2 are both forced by it. Stack it up. Every null space vector is t times 1, minus 2, 1. That's a line through the origin, a one-dimensional space. Nullity 1, exactly as rank nullity promised. Never trust it. Verify it. Multiply a by 1, minus 2, 1. Top row, 1 minus 4 plus 3 is 0. Middle, 2 minus 8 plus 6 is 0. Bottom, 1 minus 2 plus 1 is 0. It genuinely lands on the 0 vector. The basis checks out. Now let's solve a real system. Ax equals b, with b the column 1, 2, 1. Glue b onto A as an extra column, forming the augmented matrix, and reduce the whole thing together. The exact same row operations we did before carry the constants along. The last row becomes all zeros, including the constant. That's 0 equals 0, which is always true. So the system is consistent. There's no contradiction anywhere. Read the reduced rows. x1 minus x3 is 1, so x1 is 1 plus t. x2 plus 2x3 is 0, so x2 is minus 2t, and x3 is still the free variable t. Split it into two pieces, and something beautiful appears. There's a fixed particular solution, 1, 0, 0, plus t times 1, minus 2, 1. But that second piece is precisely our null space direction from before. So every solution is one particular answer, plus anything in the null space. The rank was 2, less than n, which is 3. So there's one free variable and infinitely many solutions, a whole line of them. Rank and nullity didn't just describe the system, they built its entire solution set. One more case worth seeing, because it hides a guarantee. Here's a wide matrix. 2 rows, 3 columns. More unknowns than equations. Row 2 is twice row 1, so it collapses to zeros. Just one pivot, rank 1. And nullity is 3 minus 1, which is 2. The null space is a whole plane through the origin this time. Here's the guarantee. When there are fewer rows than columns, the rank can be at most the number of rows, which is already less than n. So the nullity is always positive. There's always at least one free direction. A wide system can never have a unique solution. Only no solution, or infinitely many. But whether it's no solution or infinitely many depends entirely on b. Take b equals 1. 2. Reducing gives a harmless 0 equals 0. Consistent, infinitely many solutions. Now take b prime equals 1. 3. The same reduction gives a last row reading 0 equals 1. Impossible. That system is inconsistent. No solution at all. Your turn now. Here's a tall matrix. 3 rows, 2 columns. Pause the video and find its rank, its nullity, and its null space yourself before I walk through it. I'll wait. Here's the walkthrough. Rows 2 and 3 are just 2 and 3 times row 1, so both collapse 2 zeros. One pivot. The rank is 1. With 2 columns, the nullity is to minus 1, which is 1. For the null space, the one equation is x1 plus 2x2 is 0. So x1 is minus 2x2. Let x2 be t, and the null space is t times minus 2, 1, a line. And notice rank 1 plus nullity 1 is 2, which is n. If you got that, you've genuinely got this. Trap 1. Using the number of rows. Rank plus nullity equals n. The number of columns, never m. The rows. Count columns every time. Trap 2. Counting the non-zero rows of the original matrix. Those rows can secretly depend on each other, like our doubled row. Reduce to echelon form first, then count the pivots. And trap 3. Assuming free variables mean a solution exists. They don't. You must also check the augmented matrix. If reducing B creates a contradiction, the system is inconsistent, no matter how many free variables you have. Let's lock it in. The rank counts the pivots, the dimension the column span, the directions the matrix keeps. The nullity is the dimension of the null space. The free variables, the directions crushed to 0, and they always add to n, the number of columns. That single equation tells you whether a solution is unique, infinite, or. Once you check the augmented matrix, missing entirely. Master these 3 lines, and no linear system will surprise you again.